A rational function is a function that can be expressed as a ratio of two polynomials. In this case, f of x is going to represent two different functions in terms of a fraction. So we have some function p of x and some function q of x, where p of x and q of x are polynomials, and we're making a domain statement assumption that q of x is not going to have an x value that equals 0. Okay, so here you can kind of see two different examples that we're going to play with. So you've got your numerator being 3x plus 2 is a polynomial, denominator 4x squared minus 5x is a polynomial, and same next door. Now the interesting thing is different characteristics of the numerator and denominator will give us different components of what makes a rational function so rational. So we're going to look at different things that rational functions can tell us and where to look to find those things. So let's start with domains. Okay, we're looking at a fraction, so obviously domain is going to be related to the denominator. Let me go through the formal statement here. The domain of a rational function is all real numbers except for those values of the denominator where it's equal to 0. So denominator is equal to 0. So to determine the domain of a rational, we want to set the denominator of the rational function equal to 0 and solve for x. Any real numbers obtained. Now real does not mean like, oh, you mean unicorns and rainbows? No, I mean real numbers meaning not imaginary, so no I, but fractions, decimals, square roots, any of those. Any real numbers obtained will need to be excluded from the domain. Okay. So in each of these cases, we're going to set the denominator equal to 0 and solve. Well, technically, we're going to figure out what doesn't make the denominator equal to 0. So I want to subtract 1, and I get 2x does not equal negative 1. Divide by 2, and I get, in this case, that x cannot be negative a half. So on a number line, you think you were staring at negative a half. There's an open circle. Sorry, I can have somebody do a different color. We've got an open circle at negative a half, and we've got everything shaded on either ways of it. So we've sort of broken our domain up into two pieces. So our domain then would be anything from negative infinity out to negative a half, union negative a half up to infinity. In the next case, so we can set that equal to 0 and solve. And that's actually a good difference of two squares there. So x minus 3, x plus 3. So we get x equals 3 and negative 3. Sorry, it does not. Clarify that. We don't want those. So if I look at a number line, I'm saying that there's open circles at 3 and negative 3. And we're shading anything on either side. So I'd want to break up my domain into three pieces. So from negative infinity up till negative 3, union negative 3 to 3, and 3 out to infinity. Again, I've got three pieces in my domain statement that corresponds to the three pieces on the number line. Okay. And in the last case, x squared plus 9 equals 0. Okay, this one is not factorable. And when I solve for x, I get, let's see, I actually get imaginary numbers here. So plus or minus 3i. Okay, which then tells me that I can have any x value I want. So when I look at a number line, the whole thing is shaded. So, the whole number line is shaded, so there's no restrictions at all in this thing. So the domain can be any number for something like that. All right, so next characteristic we're going to look at are vertical asymptotes and holes. So in talking about the thing that's excluded in the domain, so now that we talked about domain, these excluded values, that means the function is not defined at that point. So the graph cannot be continuous at those excluded domain values. At the excluded domain values, the graph may have one of two things, a hole or a vertical asymptote. Okay, so let's start with this idea of an asymptote. An asymptote is a line or curve that our graph gets close to. So in other words, it approaches it, gets really, really close, but usually does not cross or touch. Let's try spelling that a little bit better. Okay, now I'm going to be really silly, and I want to get this idea of a hug in your mind, because when I'm graphing these things, eventually I'm going to say you want to hug the asymptote. So you want to get really, really close without actually touching it. So in this graph right here, in this first example, you can kind of see, oops, I meant for that to be a highlighter. Let's make that try to be a highlighter. Okay, so right there, that's an illustration of what a vertical asymptote looks like. It's a vertical line, and you can kind of see in both directions, kind of get something, you can kind of see that we're getting closer and closer to the asymptote, but we're not really actually going to touch it. We're just going to get really, really close. Okay, now the second characteristic that comes out is something called a hole. So let's go through what defines a hole. If a factor from the numerator and denominator divides out, the graph will have a hole at that excluded domain value. And so what we're going to do is we're going to factor and reduce the expression. If the factor divides out, then we're going to set that factor equal to 0 and solve for x. Then we're going to evaluate or plug in x to the reduced function to find the corresponding y value for the point y value for the point of that hole. So a hole is an actual ordered pair. It's an actual point. It's got an x value in it. Okay. Now notice in the factored form what happens here. To see how they both have x minus 1s. Okay. So what that tells me is that there's a hole at the factor x minus 1 equals 0. In other words, where x is equal to 1. So there is an ordered pair. You can kind of see it here in the picture of 1 comma something. So to find that something, I'm going to evaluate it in the reduced form. So my reduced form of my equation is x minus 3 over x plus 1. And I want to find f of 1 at there. Okay. So I'm going to plug that in. So 1 minus 3 over 1 plus 1. And that gives me negative 2 over 2, or negative 1. Okay, so there is a hole at 1 comma negative 1. Okay, so one more time, just so we can see it again. In order to find the hole only happens if a common factor divides out. We divide the common factor away, get a reduced equation, and we evaluate the x value in the reduced form to figure out the y value for that hole. A vertical asymptote. Okay, so a vertical asymptote is a vertical line where the graph approaches but never, write this really loud, never crosses or touches. So after we reduce the expression, we're going to set the remaining denominator equal to 0 and solve. This will be a vertical asymptote, and there could be several VAs. Note the graph will never, again, never cross a vertical asymptote. Never, ever, ever is it going to cross a vertical A. Okay, so in our graph here, here's sort of another illustration, something. We got a vertical asymptote there. Okay, now, not all rational functions will have a hole. Not all rational functions will have a vertical asymptote. It just so happens that in the case where it does happen, then we include it, right? But the hole comes from dividing out a common factor, and the vertical asymptote comes by looking at the denominator and setting that equal to 0 and solve. Okay? So let's take a look at an illustration of these three concepts sort of together on a couple of rational functions. So for start off with, define the domain. We're going to do this before any reducing. So before reducing, we want to look at the denominator. And it's where the denominator is going to equal 0. That's what we want to kick out. So in this case, x squared minus 1. Figure out where that's going to equal to 0, and that's the number we don't want in the domain. This one is factorable. It's a difference of 2 squares. And so, I get that x should not be equal to -1 and 1. So that's what I want to kick out. So our domain is negative infinity up till -1, union, -1 to 1, union 1 to infinity. Okay, now our holes. Our holes we find by factor, and we want to reduce. And if a factor divides out, that means there's a hole at x equals the number where it divided out. So x equals the constant where it factored out. So let's take a look at this thing then. And we already identified the denominator in its factored form as x minus 1 and x plus 1. So now we need to factor out x squared minus 2x minus 3. So that, let's see, it's got to have a 3 in it. It's got to have a 3 and a 1. I want the 3 to be minus and the 1 to be positive. Okay, so that means that the x plus 1s divide out, and I'm left with x minus 3 over x minus 1. So I now know I have a hole. Okay, so I have a hole at the thing that divided out. So if x plus 1 divided out, that means it's got to be at -1 comma something is my hole. So then I want to figure out what f of -1 is, and that's evaluating it in our reduced function here, so something minus 3 over something minus 1, and that's where I want to put that -1 at. So we get -4 over -2, which reduces down to 2. Okay, so I have a hole at the ordered pair of -1 comma 2. All right, vertical asymptote. So vertical asymptote, we want to factor and then reduce, and this time we want to look at the remaining denominator. Okay, so we're going to look at the reduced form of this, which is x minus 3 over x minus 1, and this is where I set the denominator equal to 0 and solve. So I have a VA at x equals 1. Okay, again, that's the characteristic of that rational, is that the vertical asymptote is there. But sort of identify sort of an order of ops here. We find domain first, then we factor and look for holes. If we find them, great. If we don't, that's okay. But after we identify holes, then we go on to vertical asymptotes by looking at the denominator. Okay, so in these next examples, we're going to start by, we're going to ignore the domain part for right now. Eventually we'll come back and get it, but we're just interested in the vertical asymptotes and any holes that we find. So let's start by factoring and see what we notice. So the numerator in this case factors into x minus 1 and x plus 1, and the denominator factors into x and x plus 1. And we should notice that the x plus 1s are in common, so that means we have a hole. So we have a hole at, so where would x plus 1 cross the x-axis? That's at negative 1. So at negative 1 comma something. And so I want to figure out what that is. So f of negative 1 in the non-reduced, or in the reduced form. So negative 1, so I'm going to subtract 1 off of that. So negative 1 and negative 1. Work that out. I get negative 2 over negative 1, which is positive 2. So I have a hole at the ordered pair of negative 1, 2. Then I want to look at, so now let's look at my reduced form here. Is x minus 1 over x. So the VA then would be where the denominator equals 0. So in this case, the VA happens to be 0. So we have a hole at there and a VA at there. Okay, now we're going to go into the next one. So we have 5x minus 2 up top in the numerator. Denominator we're going to try to factor. And let's see, it's got to be 3x and x. Let's see, I don't want the 2 to multiply with the 3. And I actually want the 3 to be negative, so we'll do that. So 3x plus 2 and x minus 1. Notice nothing factors out. So as far as holes go, we don't have any, right? But we do have vertical asymptotes by looking at the denominator. And that's going to be where that equals 0, so that will be at x equals negative 2/3 and x equals 1 for that one. All right, and then our last case, let's see, we can factor an x out up top. So that's 4x plus 3 over x minus 5. Nothing divides out, so as far as holes go, we have none. And then I want to look at the VAs. VAs is the denominator, and that's x minus 5, so that means we have a VA at 5. Okay, so you don't always have a hole, and if you do, find it.